Hello, everyone. My name remains Aiden. We're going to be talking today about spline interpolation. Um, so far we've talked about, so Monday we talked about floating point representations of numbers. Tuesday we talked about polynomial interpolation. And today we're kind of taking a kind of related detour from the polynomial approximations, and we're going to be talking about spline interpolation. Um, so, first of all, what is spline interpolation at all? So we're going to play the same game we played yesterday. Don't mind. It's not a problem if you weren't here yesterday, but it's the same game. It's called Connect the Dots. I'm sure most of you played it as a child. Um, So we have some points in 2D space, and we want to connect these. So these can be thought of as dots, and we want to connect these dots with a curve. Um, Per usual, we want this curve to be a function. So the function is going to take in the input x and output the output y. Now to make this a function, we need to make sure that all of the xi's are different. Otherwise, it wouldn't be a function. Um, So, um, Now, yesterday I mentioned that the easiest possible way to do this would be to just connect the dots with a series of straight lines. And I said that that is generally a bad approach. And the reason I said that is because if you do that, you end up with some spikiness, because at each of the points you're going to have uh, um, an intersection of two line segments, and those line segments are almost never going to have the same slope, and so you'll get like a spike, kind of like an absolute value of x spike. And this can be bad. However, today, all of that is forgiven. The spikiness problem, while it still is there, is just not a problem to us anymore. And now actually connecting the dots with straight lines is a great idea. um, Now, that's not quite true, but what is true is that we're basically willing to accept that there's going to be some spikiness in exchange for the benefits that this approach will give us. So let's look at those benefits. Um, this idea of just we have some dots, connect them by lines, it's very simple, but we still like to give it a name. And this is called a linear spline, or sometimes a piecewise linear spline. Though in my mind, spline and piecewise are they basically mean the same thing. So why say both of them? Um, a spline of any kind is just some systematic way of connecting dots together with curves. And yes, a curve is a line. Lines are quote unquote curves, but so we connect dots together with curves, lines, or really anything else we can get our hands on. Um, so I talked yesterday about polynomial approximation, and I said that polynomial approximation, when done right, should kind of be thought of as a gold standard for approximating functions. So why are we even trying something else? Well, there are like three good reasons. The first is that every spline we talk about today, or I should say, the first two things we're going to talk about today, at least, they require order 1 operations to evaluate. That means if I increase the number of data points, okay, this is not quite true. They actually really require order of log n operations to evaluate, but depending on how you do them, they can take O of 1 operations. So let's just say they're O of 1. And even if they're O of log n, what this means is that basically, if it's O of 1, for people who don't know, if I double the number of interpolation points, if I double the number of points that I'm trying to connect, it does not affect how quickly it takes to evaluate this spline. The log n part comes from, okay, you might need to figure out which 2 points you are between, and that using binary search would take log n operations. But as long as you know which part of the spline you're in, it's order 1 to evaluate it. This is because splines are defined what's called locally. And in particular, if we move one dot around, if we change one piece of the spline, the whole spline isn't going to change. Just parts of the spline. Usually just the parts that are directly connected to the spline are going to move around. So for instance, if I have all just straight lines connecting everything, and I move one point, only the lines connected to that point are going to change at all. And so this makes it quite fast. If you have a problem where the points that you're connecting are changing frequently, it makes it very fast to update the spline. You don't have to like recompute the whole thing every time. Whereas if you had a polynomial interpolant, you would have to recompute the entire polynomial every single time. Though if you use the barycentric interpolation formula we talked about yesterday, that's actually not much of a problem. But the local definition is somewhat useful. And much like polynomial approximants, splines can approximate any, quote, nice function. However, they also can fit data that we didn't talk about yesterday, which is in this case derivative data. So this is data not only about where the function is, but where the function that we're trying to approximate is going. This class is listed as not needing calculus knowledge, but if you know some calculus, that'll make sense. And if you don't know some calculus, then I hope the intuition that that it's not just where the function is, but where the function is going is good enough. Let's first discuss linear splines. In my mind, linear splines are actually the most useful splines we've got, because if you really need a smooth function, I would almost always use a polynomial, and if we don't care about a smooth function, well, just use lines. It's very fast. For a linear spline, evaluating the spline is very easy and very cheap. We're going to assume that the points are in order from left to right. So the first x is on the left and the last xn is on the right. And so to evaluate the spline, we just need to figure out which line segment we're on. This can be done very efficiently with binary search. Because our list is sorted, if we have a point x and we want to find which 2 points it's between, just cut the list in half and then check if the point on the left is smaller than x, and then if it is, then we know that the point must be in the interval to the right. And so we just keep subdividing our list over and over again until there are exactly 2 things, one smaller and one bigger, and that's the interval that we're in. So evaluating a linear spline that we know nothing else about is going to be order log n evaluations, which is pretty good. I want to kind of demonstrate this in Paint, good old MS Paint. So let me switch my screen. Okay, can everyone see my paint? Wonderful. Okay, so I have this number line here, and then let's say these are my points. Like this, and I connect them with straight lines. And let's say that I want to evaluate this point here. I want to plug in this value here to this function and figure out what the value is. So I basically want this value. Well, again, strictly speaking, first I need to be able to know which interval it's in. I have 5 x values, 1, 2, 3, 4, 5. So I first look at the third one, and I ask, is the point we want to evaluate bigger or smaller than it? It's bigger. So now I look in these two, and I check this. I say, is the point we're looking for bigger or smaller than it? It's bigger. Okay, well now there's only these 2 points left. We do check to make sure it's not out here, and it's not, so it must be in this thing. And then, well, we have this line, and I hope you all learned the following formula for a line. Y minus y0 equals mx minus x0. This is the point slope formula for a line. And well, we can determine the slope using these 2 points here. And we can just pick either one of these points to be our point, and then we have the point slope formula. And so this is exactly what we get. Once we know what line segment we're in, we just use the point slope formula for a line to evaluate the piecewise linear interpolant, namely that line at that point. So that's why it's pretty fast. Are there any questions about how we evaluate piecewise linear splines? Okay. We can kind of see why evaluating splines is so fast just by looking at this formula. In the formula, the only 2 points we care about are the left point and the right point. We don't care about any of the other points defining our spline. So the number of them that there are won't change anything except for how long it takes to find the interval we're in. And again, through the power of binary search, that's going to be order of log n, and log grows very, very slowly. So if we have if we had 10 points and we had 100 points, so 10 times more points, we would expect, actually I should say, if we had 8 points and we had 16 points, no, we had 8 points, we had 60, sorry. If we had 8 points, we had 64 points, we would expect that to take only 2 times longer. So we squared the number of points and it only took twice as long. So that's pretty good. This whole series is about approximation theory, and as I keep saying over and over again, the main point of approximation theory is to take an object that we don't understand very well and approximate it with an object that we do. A bunch of points connected by lines is a pretty easily understood object. And so, how do we take a function and approximate it with a linear spline? Well, here's kind of the method, or here's one method. So we want to approximate our function on some interval from a to b. Now, this might seem like a pretty strong assumption, but normally we think of functions as being on the whole number line. However, we're working with computers. They only have finite memory. We already aren't working with the whole real number line. At most, we're working with all possible floating point numbers, right? So approximating on an interval is all we'll ever need to do. And so it's a totally fine thing to assume that we're just working on some interval from a to b. And so this interval is just all the numbers from a, which is assumed to be smaller than b. So it's all the numbers from a to b. Okay, well, kind of the idea is we start by just plugging in the function values at a and b, and then drawing a line between them. So I will demonstrate this visually yet again in Paint. Changing windows. Paint. Okay. So we have some function. I'm going to draw it in blue. And remember, um, well, basically, assume that we do not actually see this whole curve. In order to get this curve, we would have to evaluate the function at every single point between A and B. And there are an infinite number of those points, so we actually don't have this curve. In order to get any one point on this curve, we'd have to plug in x. So pretend we don't see it at all. So the strategy is, I just pick the endpoints, I evaluate the function, and now I know those 2 points. Well, okay, what's the best I can do? Well, the best thing I can do is to just connect these 2 points with a line. And this gives us this gives us a linear spline. Now this linear spline is kind of awful. So we want to refine it. We want to make it better. How do we do that? Well, the method I propose is, let's just randomly pick another point between A and B. Say it's here. Call it C. So this is A, this is B, this is C. And now we evaluate the function here. Oh my, this is a pretty big gap. Oh, actually, my slide has the wrong formula for computing this. That's okay. I will demonstrate the correct one and then correct my slide later. Okay, so I evaluated the function at this point. I got this distance, and we're going to set some tolerance, maybe 10 to the minus 6 as our tolerance. So we want this distance here to be less than 10 to the minus 6. And let's just say it isn't, because that doesn't look very small. That looks like a pretty big distance. Okay, what that means is our approximation is pretty bad. So let's refine our approximation. And, well, we already evaluated the function, so let's use that function evaluation and use it to make a new linear spline, one that goes through now 3 points. Okay? Well, now we have 2 new intervals, the one from A to C and the one from C to B. And so we can zoom in on both of these intervals, and we can do this process again. Randomly pick a point between, for instance, A and C. Let's say it goes here. Evaluate the function. Compute this distance from this to the line. Realize it's bigger than 10 to the 6th. And use that to refine our spline. Like this. So now we have a spline with 3 lines going through 4 points. And we keep doing this over and over and over again, every time iteratively refining our spline. And we only stop when that distance is less than 10 to the minus 6th. Now, even if it is less than 10 to the minus 6th, we'll still refine the spline, but then we'll stop. So if I evaluated here, and maybe that was 10 to the minus 6th away, I still wouldn't waste that function evaluation. I would still make the spline bigger, but then I just wouldn't refine those anymore. So this is what I call the randomized linear spline. Are there any questions about the randomized linear spline procedure? Okay. I think there's at least one good question, which is, why am I randomly picking the points? Okay, this is another question. How do we distribute the points, and then why am I doing it randomly at all? In this case, I assume you're just picking them what's called uniformly at random. So there's basically an equal likelihood across the whole range of the of points. You kind of just like pick a number between 0 and 1, and then you go that percent between A and B. Um, so why do that? Um, well, so you can tweak it. So one thing you could do is you could just always subdivide the interval in half. This method has an advantage, namely it is deterministic. So you're always going to, on the same function, you would always end up making the exact same spline. However, there are lots of functions that we use commonly that have what's called periods. They have like a periodic oscillation. And it is not infrequent for those to have a periodic oscillation like halfway through the interval. So for instance, if I was approximating a function that does this, and assume this is perfectly halfway through, what that would tell me is, as far as my linear approximation is concerned, that's dead on the money. There's no error there. And in doing so, I have missed these two giant regions where there was a lot of error. So basically, if you always subdivide in half, there are classes of functions where this will just never work. Whereas if we kind of pick randomly, we're far more likely in this case to have randomly picked in one of these two giant regions where the error would have been big than to have picked in one of these three very small regions where the error would have been small. And so we're kind of relying on that, the fact that there is a bigger target to hit than there is, if our line is a bad approximation, then by definition of a bad approximation, the area that we could hit with a random choice where it would be a bad approximation has to be bigger than the area where it was a good approximation. The better we make our approximation, the less likely we are to hit an area with big error, which is the goal. We want this process to terminate. And actually, it's guaranteed to terminate as long as your function is continuous, which is to say as long as you can draw your function without lifting your pen or pencil, or in my case, my finger. Yes, so Borb has pointed out what a function. You could have a function that's just like. No, I don't want to save. I never want to save. That was an accident. You could have a function that's basically like, woo, has some big spike. And for that kind of function, your piecewise, your random thing probably would fail. However, these types of functions occur less often, and often when they do occur, you know about them already. But the thing is, a function like this, there's essentially no good way of catching it. Because, well, like think about a function that's just flat, then has a massive, very short spike, and then is completely flat. Unless we get, even if we subdivide in half, if the half misses it here, then we're just never going to see this spike. And so, we kind of can't plan around the spike. But we can plan around these more common like oscillations and periodic oscillations, which is why I like to use the randomized piecewise linear spline. I keep saying piecewise linear, even though I said I don't like it. Anyway, switch back to my lecture slides. Again, my slides I actually have the wrong formula for determining the error. It should be it's not this error. It should be the error between the f of c and the line. Um, so this is the randomized linear spline, yes, I've actually used this exact method before, both the subdividing in half and the random linear spline. I use them pretty often. And the randomness is actually, is genuinely beneficial. It prevents some edge cases where things can go bad. You can play with the random generator. One good option potentially would be to switch to like a normal distribution where you're more likely to have sampled near the middle, instead of a uniform distribution where you're equally likely to have sampled near the middle as near the edges. But just play around with it, see what works for your problem, see what works for your application. There's something, if we knew a little bit more about our function, there's something we could do that's potentially better. There's something called a Lipschitz constant. If we know the function's Lipschitz constant, it basically tells us how quickly the function can change. And if we know that, we can just subdivide our intervals until we get intervals smaller than a certain size, and then using the Lipschitz constant, you're guaranteed that you're that went out briefly, but I am back. I should be back. Yeah, so if you know the Lipschitz constant, you can do better, but we can't assume you know the Lipschitz constant because, like, how would you even calculate the Lipschitz constant? It's a good question, but we'll assume we don't know it and move on. So, well, in terms of like applications and in terms of like distance you can go with a spline, the linear spline actually is like remarkably good. But sometimes we have more data that we need to fit. In this case, the way I've described it, so if you look at a curve, at any given point, a curve has a tangent line. You should have learned this in algebra or geometry. So there's always a line that like just barely touches the curve. Sometimes you need to match the slope of this line. This basically tells you not only where the function is, but where the function is going. And this slope value is a number. Now, we've been using lines, and lines encode two pieces of information. If you write a line mx plus b, it's only got two numbers, m and b. But now I'm giving you four pieces of information. I'm giving you where the function is on the left, where the function is on the right, the slope of the tangent line on the left, and the slope of the tangent line on the right. And that's four pieces of information. A line only can encode two pieces of information, so a line won't cut it. So we need to use something that encodes four pieces of information, and for that we're going to use a cubic polynomial. I said once great choice instead of one, not sure why. But a cubic polynomial encodes four pieces of information, namely its four coefficients. And so this will give us what's called a cubic Hermite or Hermite spline. And I want to, again, cut back to paint real quickly to kind of describe the scenario in a little bit more detail. The real paint heavy lecture. Okay, so basically what I'm saying is, instead of my data just being points, like this, I'm saying not only are these points, but I also want the function to be going like this here, and going down like this here. Well, okay, so I could, if I draw a straight line, then like that's not that's not going the same direction. These are going completely different directions. But what I could do is I could draw a curve that looks kind of like this, and then goes like this. And hey, look, these kind of match up here, and these match up here. And so this is the goal, to make something that matches all four of these things at the same time. It turns out the magnitude doesn't matter. In 3D it matters. In 1D it does not matter. So yeah, this is just the slope of this tangent line. It has nothing to do with the magnitude of those direction vectors. Yeah, and so this leads to us to this thing called a cubic Hermite spline. What if I want the curve to point up more? You would just change the slope. You wouldn't change the size of the vector, because the vector was just a visual representation of the tangent line. You would just change the slope of the tangent line. Now, if you wanted it to be following the function tangent line for longer, like if you wanted it to like hug the tangent line more, you'd have to do some exotic stuff. But this is just a way of matching the tangent line data at the endpoints. And so, I talked yesterday about wanting to avoid like this thing I called the monomial basis, or also known as writing down the coefficients of a polynomial. And so we're actually going to construct our cubic function using these four other cubic functions that we're going to add together. And so here are the four functions. They look like this. Why those were chosen is a great question that we're not going to get into exactly right now. Actually, we're not really going to get into it all. But it turns out, if you have these two pieces of data, you have x, y, and then the tangent line slope, and you have x, y, and the tangent line slope on the left and the right. This polynomial p of x will get you from the left to the right, matching all of that data. Now I've kind of chosen to give you the big, beefy formula and not the kind of nice, simple formula that happens if you choose x0 to be 0 and x1 to be 1. But this is the formula that connects any 2 points, x0 and x1. Does this make sense? The whole like data thing, I mean, in the thing that I drew earlier, the x's are just the positions on the x-axis, the y's are just the positions on the y-axis, and then the z's are the slopes of those arrows that I drew. So on every endpoint, I have 3 pieces of data, not just like 4. Oh, sorry, not 2 like I had last time. Okay, so this does the job. It's kind of a little bit of a letdown. We don't have the tools or the time to really derive why you pick these numbers. And why you pick these polynomials, but you do. And, if you want to be very efficient, you work out some efficient way of evaluating these 4 polynomials. and then evaluating the resulting polynomial is pretty easy. It's just constant multiples of these four what are called basis polynomials. Are there any questions about that? Well, I can get to that in a bit. Well, actually, I kind of can't, but so strictly speaking, they're what's called a spline basis. So they're not really. It's like they're like a what's called a basis of like all the polynomials of all cubic polynomials going from x0 to x1. I mean, which ends up giving you all of them, but they're specifically chosen to go from basically 0 to 1. No. Okay. So, I've only given you a formula for going between 2 points, right? But just like with the lines, the piece with a linear spline, as long as you can go between 2 points, you can just chain together a bunch of these to make a spline. So if I again switch back to paint, I had this line here, but what I could do is I could add another point here and say that it wants to go down here. And well, now I have a curve that looks like this. Okay, maybe I have a point here and it wants to go up like this. Well, now I add the curve on that goes like this. And you can see that I've, by using this trick that can match these 4 pieces of data, I can make splines. And exactly like with the linear spline, all I have to do, if I have an x input, is figure out which of these intervals I'm in, and then use my one formula, which is a cubic polynomial, to evaluate the value. So, if I was here, I could just look right here, and then I would be between these 2 points. And so evaluating would just be an application of the Hermite-Spline formula. So it is really quite simple at the end of the day. And again, this is why it's essentially constant time to evaluate. It might take it might take log n to figure out where the point is, but once you figure out where the point is, you're just evaluating a cubic polynomial. You don't care about how many other points there are. And this is that great locality property that we talked about at the very beginning, where splines are kind of defined locally. Okay, back to the slides. Okay. So I kind of went over some of this. So, you can use this formula to connect, all these different kinds of data points. Now, sometimes you won't be given those tangent line slopes, but you still might want, this curve instead of these, a bunch of straight lines for your spline. And one nice thing about a Hermite spline is that it will give you this nice smooth curve. And so the slopes, that slope information, talking about how to get it requires calculus, but kind of two most common cases are either you've just been given the slope and then you're trying to match it, or you've computed that slope from the original function using calculus. Or the third option is you just kind of guessed, or you just made one up. The first two of these is just usually called a Hermite or Hermite spline, and the second one actually gives you what's called the Catmull-Rom spline. Depending on what method you use to guess, you either get a Catmull-Rom spline or something called like a canonical spline. But the Catmull-Rom spline is the most common, and Ethan has a Catmull-Rom spline library type thing in Roblox, which is kind of cool. Now, one thing about Hermite splines that can happen is you can get some weird oscillations. And so if you want to make sure that you completely avoid those, you either have to change your approach, or you can go back to using the straight lines, because the straight lines will never have weird, strange wobbles. Andrew, there's it's called, I think it's just called Catmull, and then Ethan published it. It's like a Roblox module or something. Not my expertise. Just Catmull, like the name on the screen. Or CatRom, thank you. Thank you for posting that. Okay. So moving on. So I've really only talked about this like 1D problem of like having one input and one output. But sometimes you want to make curves, in 3 dimensions. This comes up a lot in Roblox, especially because you're almost always working in a 3D environment. And there's this like one simple trick to take all these methods and apply them in 3D, which is you just break them into the X direction, the Y direction, and the Z direction. If you want a spline connecting points in 3 dimensions, you just make 3 splines connecting all the 1D stuff and you stick them all together. It is kind of just that easy. Now, this is all assuming that you take in one real number and output a vector 3 in this case. But you could try and take in a vector and output a vector as well, in which case this gets a little bit more complicated. But for now, we're just talking about these nice curves in 1D, these 1D curves in like 3D space, in which case everything boils down to just working in components. So it is kind of simple. Now, Bezier curves. Bezier curves are a little bit weird for me. They're very commonly used in certain areas and essentially never used in others. I have never used a Bezier curve for any practical application. That is not to say they do not have practical applications, but they're not something that I encounter very often. Because they're basically only used in like computer graphics and in like computer-aided design. There are some uses outside of that, but they're not very common. And this is kind of for historical reasons. The Bezier curve was invented by designers, people designing, I think, cars, to make interesting and cool curves. It wasn't really designed as a mathematical or numerical tool. And so they're a little bit complicated to talk about for me. So in particular, we call, like, instead of having like what I would call interpolating nodes, which are these data points that we have to go through, Bezier curves have these control points. So if you have an endpoint, so I give the formula here for this like endpoint Bezier curve, which is a curve defined with n control points, and it has this interesting recursive definition. What you should note in equation 10 is, if you've heard of lerp, this is just lerp. And what lerp is it's a weighted average. So basically, to compute a Bezier curve with endpoints, you take a weighted average between two Bezier curves with n minus 1 points. And you do this recursively. So it's basically this giant average you're taking. You're taking this massive weighted average whenever you want to compute the value of the Bezier curve. And so, well, sorry. My bad. I have a cough. No, they're iterating by a stride of 1. Thank you. So basically, for the first curve, you took the last point off, and for the second curve, you took the first point off. I believe that's the correct formula. Well, I was going to show you the Wikipedia page for Bezier curves because they have cool visualizations that I couldn't make. So we can also check the formula. But like this process here, I'm not sure how well you can see it. On the bottom, like this is a 1, 2, 3, 4, 5, 6 point Bezier curve. So you can see it has 6 control points, and there's a bunch of these averages going on. Yeah, so the red line is the actual resulting curve, and each of the other lines are just the weighted averages happening. And they do make genuinely very cool curves, and they can do weird, cool things. But, in all honesty, the coolest thing about a Bezier curve is once you know how a Bezier curve works, they're pretty intuitive, and they're like, by messing with the control points, you can make these interesting curves yourself. So from my perspective, the best thing about a Bezier curve is that they're really great for design. They're really great for designers, and they make these really natural looking curves. But mathematically, they're not as interesting. At least not as interesting to me. I'm sure there are some computer graphics people who would be able to tell me all sorts of interesting math you can do with Bezier curves. But, to me, that's not like the main point of them. The main point is, of all of these, yes, of all of these curves, they're kind of the most intuitive to use. Now, something you will have noticed, the curve does connect the first and the last point, but it never reached any of the other points, any of the other control points. And it basically never will. Unless you perfectly set it up to make it do that, it will essentially never connect it'll never hit any point other than the first and last thing. So to make a spline, you actually have to patch a bunch of these Bezier curves together to get a Bezier spline. And there's not much interesting stuff I can say about Bezier splines, because anything you could do to make them interesting would also restrict your ability to change the curves. Like in order to make them, for instance, line up at the points, you'd have to restrict the Bezier curve points at the ends, and then you're not able to essentially warp them and change them and curve them however you want, which is kind of the whole point. Yeah. One thing that does happen is like the curve will end up lying in this thing called the convex hull of your points, meaning essentially if you make a polygon out of all the points, then the curve will end up lying inside that polygon. That is one interesting mathematical property, but other than that, I don't really know of any. And actually, that fact follows from the fact that it's this big weighted average. But yeah, that's Bezier curves from my perspective. I think they're very useful and very cool, but not for my purposes. So go out and do cool, weird things with them, but I can't really offer much in the way of help with those. Yeah, so that's the talk on splines. Tomorrow we're going to be talking about least squared regression, which is another cool topic. So far, basically what we've done is all the methods that we've worked with have essentially trusted the data we've been given. We've been given this data, and then we've interpolated through it, and we've always made sure that we hit the data points exactly. Least squares is going to, and least squared regression is basically going to answer the question, what if we don't actually trust the data we've been given? And then, it's not as important that we actually go through the data as that we basically hit the average of the data. And so we'll be going over methods in that. And then on Friday, we'll get to the last topic, which is numerical integration and differentiation, where we're going to talk about, well, actually, we'll come back to cat-Rom splines specifically, and also talk about ways of computing things like that. So, are there any questions about the spline stuff we've talked about today? I mentioned RBX Math yesterday, which is our fledgling math repository. Ethan handles the spline stuff mostly, though I have implemented the linear splines for another application. So linear splines are kind of in there already. The spline stuff just doesn't super work so far, but the cat-Rom does work. Bohr asks, how do you pick between cat-Rom and Hermite splines? The answer is essentially, if you know the tangent lines, use a Hermite spline. If you don't know the tangent lines, but you still want a nice smooth curve, you use a Catmull-Rom spline. Because a Catmull-Rom spline essentially uses the points to guess what the tangent line would be. So it basically makes up new data and then fits it. So if you have the data, use a Hermite spline. If you don't have the data, use a Catmull-Rom spline, which is exactly what the benefit of a Catmull-Rom spline is. You give it the exact same data you would give the linear spline, and then it still gives you a nice smooth curve instead of this jagged thing. Though it can do some weird, unpredictable stuff sometimes. I don't have a list of splines. They exist. I mean, so there are like two main kinds of splines. There are Hermite splines and there are B splines. So those are like the big classes of splines that I would look up. Hermite splines are designed to fit any amount of derivative data, so you actually can do second derivatives, third derivatives, etc. And then B splines are basically kind of more of a mathematical construction of splines, where we basically do some linear algebra to compute what's called a spline basis, which is where the B comes from, a basis splines. Yeah, B spline, literally. So yeah, and they're kind of well, whenever I do math with splines, I use B splines, and then whenever I do implementation, I don't use them because they're not as useful. Oh, sorry, someone asked, is cat-ROM performance efficient? Yeah, cat-ROM splines are super efficient. Again, well, they're like at worst they're at worst they're log n to evaluate, and at best they're order one. You know, this step of having to figure out what um, bin you're in, you only have to do that if you're not sampling at regular intervals. But if you do sample at regular intervals, like every single data point has the same distance between it, you can just do a single calculation to figure out which bin you're in. You just do like a modular calculation, and then you know exactly what bin you're in. So a Catmull-ROM spline and a Hermite spline will evaluate in roughly the same amount of time. Hermite will just match. It basically, like, think about it this way. They're roughly the same to actually compute, but a Hermite spline will approximate the underlying function better because you know more data about that function. And the more data you know about a function, the better it should work. So Hermite basically assumes that you know the data perfectly, and cat-ROM says, meh, don't really know, figure it out later.